So we're going to today apply multiplying monomials and polynomials in area problems. As you've long known, to find the area of a rectangle, we multiply length times width. And in most of the problems that we're doing, the most basic kinds of problems, we have an original rectangle, or a rectangle. I'm going to call it the original, but I'm going to abbreviate that. And then I'm going to call the other one the new. If you remember from our earlier study of charts, we need to find these four boxes first, and the variable can only go in one of these two columns. So let's just start at the beginning and look and see what we can find out. A rectangle is 5 centimeters longer than it is wide. Going back to our earlier tricks for word problems, we almost always, the last variable mentioned, we don't know the length or the width. And when they are compared, wide comes after longer. So almost always in the English language, that makes it easier to have the variable be representing the last one mentioned. So if the width of the original, a rectangle, is 5 centimeters longer than it is wide, and we're calling the width x, the length will be x plus 5. Now, if the length and the width are both increased by 3, let's stop and pause and see what that means about our chart. The width is already x, so to increase that by 3 would make it x plus 3. The length, however, is x plus 5. To increase that by 3 makes it x plus 8, because 5 plus 3 is 8. So we've accomplished getting these four boxes filled in. And you know from years of experience that length times width equals area. So x times x plus 5 will be the area of the first rectangle. Notice I can put the x in front of the x plus 5 because of the commutative property of multiplication. It tells me I can multiply any numbers. So if I say to you 2 times 6, that's the same as 6 times 2. Order doesn't change the product of numbers. So by the same property, if I want to say x plus 5 times x, that's the same as x times x plus 5. And the way I have it written now is closer to the way that you're used to being able to recognize and multiply. We also know that in the new rectangle, the length is x plus 8, and that quantity needs to be multiplied by the width, x plus 3, to get the area. I've succeeded in filling in the chart. However, to get the equation, we need to think about these areas. We've got the area of the original rectangle, and then we know each dimension, the length and the width both, are increased by 3. So clearly, this is a bigger rectangle than this. How much bigger? Well, the problem says that the area is increased by 60 square centimeters, is just the units. So x times x plus 5 doesn't equal x plus 8 times x plus 3, but we do know how they relate. We know the new rectangle is 60 more than the original. So if I add 60 to this one, then I do have an equal, I do have an equation that makes sense with the facts of the problem. So let's go ahead and solve that. Right now we know that x times x plus 5, or the original rectangle, has 60 square centimeters added to it when the length and the width are both increased by 3. This goes back to the chart. So now it's just a matter of doing the computation and the solving. Here we have to distribute the x over both terms, giving us x squared plus 5x, and then plus 60. And over here, just like last night's homework, we have to distribute each term of the first polynomial over each term of the second, giving me x squared plus 3x, and then back to do plus 8x plus 24. Before I move on to solve, I want to simplify that right side of the equation. X squared plus 11x plus 24. So, when solving, this is why I call these convenient quadratic equations, because the quadratic terms cancel each other out, leaving us with a standard equation with the variable on both sides. So we need to bring the variables to one side and the numbers to the other. And that gives me 6x is equal to 36, which makes x equal 6. We're not looking at the original chart right now, but if I did, I would see that the length is 5 more than the width. The width is what we called x. So x equals the width. That's 6 centimeters. And the length was x plus 5. X plus 5, so this is the width. That's what we said the variable was going to represent. And now that makes this one 11. That's the length, because that's how we set it up in the chart. That's like our key telling us what it is that we have found. So the original dimensions are 6 centimeters by 11 centimeters. Sometimes things get a little bit trickier. If it says there's a rectangular fish pond. Okay, this is harder than you need it to do. Never mind that problem. Mostly, that's what you need to know. It is sometimes valuable to understand that if, I don't know, if the dimensions of this are 10 by 6, if I put a 2-inch or 2-foot something, if I'm adding something around it that is 2 inches or 2 feet or whatever this denomination is, there's a 2 here, and a 2 here, and a 2 here, and a 2 here, and there's also a 2 here, 2 here, so on and so forth. So this 10, you have to add 2 this way and 2 this way, making it 14. And this 6 has 2 and 2, making it 10. So a 2-foot border adds 4 feet to each dimension. Usually, if you have a trickier problem, that's the kind of extension there is. So good luck with these, as well as your practice with further quadratic equations. Actually, before we leave, let's sum up what we do on these. The first thing you want to do is fill in the boxes for length and width. Only one can be represented by the variable. The others in terms of the variable. Which just means using the variable. Goes without saying, you need to make a chart. Okay. Second step is to multiply length times width, make it a little fancier, to get the area, a variable expression for the area. For each area, I should say. Then check back with the problem to see how these areas relate. And write an equation to fit the facts. In other words, if the area has been increased by 20 square units, then you want to add 20 square units to the smaller one so that it will equal the bigger one. If it's been decreased, similarly, you would subtract units of area so that to make them equal. Sometimes they're set up so that they equal each other. I do think with practice, though, these are not the hardest of chart problems, so I hope these go well for you.